In this video, we're returning to finish the last part of example 2. So we have the same vector field D from the previous video, and now we want to find a unit vector at P, which is perpendicular to D and tangential to the cone theta equals 150 degrees. So we've got a lot going on here. So first, let's remind ourselves of our result from part 1. So this is our value of D at point P. So we're going to need that because we want our unit vector to be perpendicular to D at point P. But then let's kind of break this problem statement down and figure out exactly what we want. First of all, note that we want a unit vector, but that's not too difficult. That's not going to add a whole lot of work. So let's find a vector first, and then we can make it a unit vector later. So find vector first, unit vector later on. Okay, so now we're talking about this cone at theta equals 150. So we kind of talked about constant coordinate surfaces. So for theta, remember it's defined as the angle coming down from our z-axis. So if we go 150, we've gone past 90, so we get something that looks like this, and then we spin it around for all phi, we go all r values, and we're going to end up getting a cone that looks something like this. Now our theta unit vector is going to be in this direction here, sort of pointing towards the middle of the cone. So this is our use of theta. And so let's remind ourselves we want something that is tangential to this cone, so sort of along the surface of the cone, but perpendicular to our D at that point P. Okay, well, if we want something that is tangential here, so let's say tangential to cone, really that's the same as being perpendicular to this unit vector here. So tangential to cone is same as being perpendicular to a vector that is normal to the cone. And so of course as we would expect, our unit vector in the theta direction is perpendicular to our cone surface, theta equals 150. Okay, so we know that we want something to be perpendicular to our u of theta. We also want it to be perpendicular to our D at point P. So if we want something to be perpendicular to two vectors, we can think back to our previous unit, and we know that our cross product gives us just such a thing. So if we have A cross P, we know that the result is going to be perpendicular to both of those. So we can then say, well, let's look at D cross our unit vector in the theta direction. And what that's going to be is U unit vector in our R direction, unit vector in theta, unit vector in phi for our first row. Our second row is going to be D, so -5, -0.0433, and 100 because we've evaluated at point P. Our unit vector in the theta direction is just 0 in R, 1 in theta, and 0 in phi. So evaluating that, we get -100 in our R direction, -5 in our phi direction. Okay, and so it's worth noting, of course, we could have also swapped the order of these two. We could have done the unit vector cross D, and we would have just gotten +100 in our R direction, +5 in our phi direction, but ultimately the same result. So now we want to go back and say, well, we wanted a unit vector, so let's convert this vector, which is perpendicular to our D and parallel or tangential to our cone surface, to a unit vector. So to do that, we can say our unit vector is equal to the vector itself divided by the vector's magnitude. So we have -100 in our R direction, -5 in our phi direction, divided by the magnitude, which is just square root of the sum of the squares. So we have -100 squared plus -5 squared, and then square root of all of that. And we get that that is approximately -0.999 in our R direction minus 0.0499 in our phi direction. And that is our answer for part 3, and that concludes our second unit on coordinate systems.